Hello, I'm going to be doing proof 21.2, which proves three things. That d of f is equal to the work form of the gradient of f. That d of the work form of f is equal to the flux form of the curl of f. And that the flux form of d of the flux form of f is equal to the mass form of the divergence of f. So before we do any of that, I'm going to draw a diagram. So a function and a zero form are the same thing. To go from a function to a vector field, that is you do that by taking the gradient. And to go from a vector field to a one-form field, you do that by taking the work form. And also to go from a zero form to a one form just by the operator d. So this means that d of f is equal to the work form of the gradient of f. To go from a vector field to another vector field, you do that by taking the curl. And to go from a vector field to a two form, you do that by taking the flux form. And to go from a one-form field to a two-form field is by the operator d. So d of the work form of f is equal to the flux form of the curl of f. And then to go from a vector field back to a function, you do that by taking the divergence. To go from a function to a three form, you do that by taking the mass form. And to go from a two form to a three form is also by the operator d. So d of the flux form of f is equal to the mass form of the divergence of. So this is the three things I'm going to be proving. I'm going to erase it now because it takes up too much space. So the first thing I'm going to be proving, part A, is that the work form of the gradient of f is equal to df. So gradient of f is equal to the derivative with respect to x of f, derivative with respect to y of f, and the derivative with respect to z of f, a column vector. So the work form of the gradient of f is equal to dx of f dx plus the derivative with respect to y of f dy plus the derivative with respect to z of f dz, which we know is equal to d of f. So proof first part, done. Second part, part B. I'm going to prove that the derivative of the work form of f is equal to the flux form of the curl of f. So the work form of f is equal to f of x dx plus f of y dy plus f of z dz. So if we take the exterior derivative of the work form, we're going to get 6 terms. However, I'm only going to deal with 2 because I will show that it will give the x component of the curl and the other 2 will give the y and the z components. So yeah. So if you do dy f of z, dy d wedge dz, plus dz f of y plus 4 other more terms that I'm going to ignore. If you rearrange and you combine these, you would get dy c minus dc f of y of dy wedge dz plus 2 other terms. But what you'll notice is that this is the x component of the curl. And then the other 2 terms would give the y component of the curl and the z component of the curl. So we indeed did prove that this statement, that d of the work form of f is equal to the flux form of the curl of f. So yeah, so I'm going to erase these 2 things and prove the last step, so I can have more space. So the last thing I'm going to be proving is that the stereo derivative of the flux form of f is equal to the mass form of the divergence. So the flux form of f is equal to f of x dy wedge dz plus f of y dz wedge dx plus f of z dx wedge dy. So if you take the exterior derivative of this, you get the flux form is equal to dx f of x plus dy f of y plus dz f of z with a dx wedge dy wedge dz. So if you took this derivative with respect to x, you would get dx wedge dy wedge dz. This with respect to y, you get dy wedge dz wedge dx. If you rearrange them, there's 2 switches, so it's still positive. Same for this one, it'll be out of order, but there's 2 switches, so it's still positive. So this is what you end up getting, dx wedge, dx, exterior, the derivative with respect to x of f of x, plus the derivative with respect to y of f of y, plus the derivative with respect to z of f of z. Which you'll notice is the divergence of f, so this is actually equal to the mass form of the divergence of f. So, yeah, that's it.